Hey guys, tonight we drift gently into the very beginning of everything you can imagine, a universe freshly awoken from silence. You probably won't survive this if by survive, you mean trying to grasp the scale of what you're about. To see, because even a single light year can make your brain ache with wonder. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, post your location and local time in the comments. I want to know where we're all drifting together tonight. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You trudge through a black void, the kind that isn't quite empty, but hums softly with the potential of everything to come. There's no sound, no air, no gravity like you know it. Just the dim flicker of the first photons, those tiny energetic messengers daring to move outward from the singularity's last gasp. Imagine, if you can, a dark sea punctuated with sparks so faint you almost doubt they exist. These are the first lights, traveling across a void that stretches infinitely, carrying whispers of the universe's infancy. You might imagine it as the softest fireworks show ever, where each explosion is subtle, shy, almost apologetic for waking the cosmos. Historians and physicists still argue whether the initial burst was perfectly uniform or lumpy with hidden currents, little eddies of density that would one day decide the shape of galaxies. Tiny clumps of matter begin to settle, influenced by gravity's first coaxing touch. Dust, hydrogen, helium, and trace lithium swirl slowly together, like dancers moving in a ballroom without music. You can almost feel the tug of attraction, gentle, irresistible, the kind that makes you lean toward a friend in a crowded room without even noticing. Oddly, some pockets are denser than others, and these spots will eventually become the seeds of stars and planets. Fringe theories whisper about invisible primordial black holes that might have formed in the cracks of this young universe. Tiny creatures of gravity hiding in plain sight. It's the sort of idea that makes you raise one eyebrow because it seems to contradict all the neat pictures of smooth cosmic evolution you've memorized in textbooks. You float past clumps of gas, and their faint glow begins to warm your perception. A gentle reminder that light exists even in the emptiest void. The universe is expanding, faster than you can imagine, though you're moving so slowly, suspended in time, that you don't feel it. Imagine standing on a beach as the tide pulls sand grains apart, but instead of water, it's space itself. Stretching, and instead of sand, it's matter that will one day become stars, planets, and maybe someone's late-night snack. Quirky fact. The very first atoms didn't form until nearly 380,000 years after the initial expansion. So for a while, the universe was basically a soup of particles too shy to bond. You drift past this cosmic stew, noticing the subtle dance of protons and electrons finally pairing up, letting photons slip free, giving rise to the first afterglow of light we call the cosmic microwave background. You shiver with a curious thrill, imagining that the glow you see is still around, billions of years later, wrapping our entire galaxy in its ancient whisper. The darkness is not lonely, though. Tiny fluctuations in density hint at the patterns to come, as if the universe doodles before it decides on architecture. You float through these ripples, feeling almost parental, like watching a child stir their finger in pudding, not knowing yet what they'll draw. Historians still argue whether dark energy's influence was already subtly guiding these early motions, a phantom presence shaping expansion before anyone could measure it. You yawn into the void, letting the soft hum of cosmic formation soothe you, noticing the gentle randomness of these first moments. Every particle and wave a participant in a ballet choreographed by forces so slow you might doze mid-step. Past the faintest wisp of what will become a nebula, glowing softly in blues and reds you can barely perceive because the light is stretched and dimmed over billions of years. Fringe astronomers suggest that tiny magnetic fields already threading through the primordial plasma could have nudged some of this matter into spirals before stars even existed. You consider this while stretching, letting the thought drift past. You like a balloon in zero gravity. These fields are invisible, subtle, and utterly unassuming, yet they might have quietly dictated the grand layout of galaxies before the first stars even flickered. You smile, imagining a universe with invisible hands sculpting beauty, a sleepy artist drawing patterns with invisible ink. Finally, the first inklings of structure emerge, filaments connecting clumps of matter, the first hints of cosmic architecture. It's like a spider web stretching across the void, delicate yet immensely strong, its strands brimming with potential. You float along one of these strands, noticing the gentle pull toward denser regions, feeling almost lulled by the slow rhythm of accumulation. The universe is alive with potential, a subtle hum in your ears, a faint warmth in your perception, even though the temperature is near absolute zero. Quirky detail: some cosmologists speculate about entire regions of the universe that might forever remain invisible to us, hidden beyond a cosmic horizon, their light never reaching these ears, like secret lullabies never sung. You feel a sense of intimacy, a quiet privilege, to witness the first cosmic moments, as though the universe whispered, "Go on, watch," but slowly. By now, the first faintly glowing knots of matter attract each other more purposefully, and gravity starts to dominate. You glide past these proto-structures, noting the almost imperceptible rotation some inherit, tiny angular momentum that will influence galaxy formation eons later. Historians still argue whether turbulence or sheer luck played the bigger role in shaping these first dense clumps. You let yourself drift in thought, pondering how these initial conditions echo in the stars overhead tonight, in the sky above your bedroom window, reminding you that the past is always present, even when you're tucked under blankets. You watch. Photons bounce free from this young universe, creating a gentle background glow, the oldest light you'll ever see. Fringe theorists suggest there could be subtle patterns in that light that tell tales of physics beyond our current understanding. You hum softly to yourself, imagining a piano tuned to cosmic frequencies, each note a whisper of creation, each vibration a lullaby for the universe itself. The hum, the faint light, the gentle tug of emerging structures, all of it invites your eyelids to droop. It's difficult not to feel sleepy when the universe itself moves with such deliberate, measured pace, every particle obediently drifting toward its destiny. And as you settle in, drifting alongside the first matter forming, you feel a connection to this vast, ancient expanse. Every flicker of faint light across the void is a reminder of beginnings, the quiet patience of cosmic forces, and the absurdly poetic fact that you exist at all, billions of years later, in a universe that started with nothing but a whisper of light and a hum of gravity. Somewhere in this gentle darkness, the seeds of stars, planets, and your own sleepy imagination are quietly, inexorably taking shape. You drift onward, leaving behind the faint glow of the first photons, and now the universe feels slightly more tangible, if still impossibly vast. Dust and gravity begin their subtle waltz, each particle tugging on the next, nudging companions ever so slightly, forming clumps that will one day become stars and planets. Imagine reaching out and feeling the gentle pull, not with your hands, but with your awareness, as though your very thoughts are drawn toward these nascent masses. Gravity is patient. It doesn't rush, yet it never stops. You probably won't survive a single encounter up close, though thankfully the universe has mercy and spreads its forces gently at first, letting you glide through the void unscathed. So lean back, breathe, and let the cosmic choreography unfold. The dust clouds are surprisingly diverse. Some are thick and sluggish, almost lazy, while others twitch with invisible currents, spinning imperceptibly as they collapse under their own weight. You can almost hear them, if you listen carefully, a soft whisper like the sigh of wind through a meadow at night. Oddly, within these clouds, tiny pockets of denser matter form faster than expected, hinting at quirks in the primordial soup, like surprise eddies in a quiet pond. Fringe theorists speculate that these overdense knots could be the first seeds for globular clusters, or perhaps even the remnants of primordial dark matter halos. But no one is quite certain. Historians of science still argue whether gravity alone sculpted these clouds, or if magnetic fields were quietly weaving threads through the dust, guiding the slow spiral of matter. You glide past filaments of gas, tracing delicate tendrils that weave into each other like lace. Within the folds, hydrogen and helium bond in tiny, imperceptible ways, setting the stage for nuclear fusion that will eventually ignite the first stars. Think of it like watching a chef knead dough, slowly, deliberately, with invisible hands shaping the final loaf. And speaking of kneading, quirky fact, some simulations suggest that tiny turbulence patterns, mere ripples of motion in the dust, can dramatically change the eventual size of the stars that form. It's as if a slight nudge in the wrong direction could produce a cosmic heavyweight champion or a timid light speck. You hum to yourself, imagining the universe as a gentle, playful experiment, testing countless possibilities while you drift unbothered. You notice that some of these dust clouds rotate almost imperceptibly. The rotation is minuscule, almost lazy, yet it matters, because angular momentum will decide whether a cloud collapses into a round star or a flattened disk, a protoplanetary nursery. Historians still argue whether all molecular clouds inherit rotation from larger galactic motion, or if some develop spin purely by chance through collisions with neighboring clouds. You float along a slowly spiraling filament, feeling the gentle tug on your consciousness, a reminder that movement, even the faintest, can dictate the shape of the future. Suddenly, pockets of denser matter glimmer faintly. These are protostars, barely more than knots of gas compressing under their own weight. You peer closer, noticing that some clouds form oddly shaped filament-like extensions, cosmic tentacles perhaps, reaching for nearby matter. Fringe astronomers propose that these shapes may hint at hidden interactions with early magnetic fields or unseen dark matter threads. You can't touch them, of course, but the visual impression alone is enough to make your eyelids flutter. It's mesmerizing, like watching smoke curl gently from a distant chimney, slow and hypnotic. Around you, the dust clouds are not entirely uniform. Some regions are rich in heavier elements, trace amounts of lithium or beryllium, remnants from the universe's earliest moments. You drift past these pockets, imagining them as tiny islands of potential, the ingredients that will one day make planets, and perhaps even life, possible. Oddly, some simulations hint that these pockets can produce small clumps that fail to ignite into stars, wandering instead as failed stars or brown dwarfs, lurking quietly, unnoticed. Historians still argue whether these rogue objects were common in the early universe or an exception, but either way, you glide by, lulled by their silent presence, and the motion is gentle. Gas streams, dust filaments, and protostellar knots move imperceptibly toward one another like dancers at a ball swaying in slow rhythm. You notice the occasional shockwave from a collapsing cloud, a ripple that compresses nearby material, nudging neighboring clumps to join the dance. Fringe theorists speculate that these microshocks could influence the distribution of star masses in ways we're only beginning to model. You imagine the universe as a conductor with infinite patience, orchestrating chaos into order, one gentle tug at a time. Even as you drift further, you can sense gravity's subtle pull everywhere. Tiny eddies of material twist and turn, slowly coalescing. Some pockets stretch into elongated shapes, forming cosmic spaghetti that will later fragment into multiple stars. Quirky detail, these formations are sometimes called filamentary, Cores by astrophysicists, a term that sounds almost like a bedtime snack rather than a crucial cosmic structure. You hum quietly at the thought, appreciating the humor in terminology that makes massive cosmic objects sound cuddly. You continue past filaments and clumps, noticing the faint interplay of pressure and gravity, heat and motion. Historians still argue whether turbulence within molecular clouds or external forces from nearby stellar explosions play the dominant role in sculpting star-forming regions. You float past these whispering nurseries, letting the complexity wash over you, feeling the gentle rhythm of matter finding its place. The clouds move with serene purpose, folding in on themselves, spinning slowly, as if the universe itself were inhaling and exhaling, a cosmic breath. Finally, you glimpse the first hints of protoplanetary disks forming around dense cores. Dust begins to settle in flattened circular patterns, the seeds of planets quietly assembling in their invisible orbits. Fringe theorists suggest that these disks could be influenced by early magnetic fields or subtle interactions with nearby protostars, nudging material ever so slightly off-center, creating eventual orbital eccentricities. You drift past these formations, marveling at the quiet patience of cosmic construction, the slow artistry that requires neither hands nor eyes, only time, gravity, and a universe content to let things unfold. You move deeper into the universe's growing complexity, leaving behind the formless dust clouds that have been dancing for eons. Ahead, the scene blooms into something far more dramatic. Nebulae, vast, colorful cradles of stars, spreading across the darkness like strokes of watercolor on black velvet. They don't roar or blaze. Instead, they glow with a soft confidence, their light drifting through space as if it has all the time in the world. You glide toward one, its reds, blues, and golds shifting subtly as if the colors themselves are drowsy. It's a good thing you're not in a hurry, because nebulae are in no rush to impress. They take millions of years to sculpt their beauty. Within this glowing expanse, you notice strange shapes. Some regions twist into spiral curls, others stretch into long, wispy tendrils. In one corner, dark lanes of dust slice through a bright region like shadowy rivers cutting across a meadow. Historians still argue whether these dark bands are purely the result of dense, light-blocking dust, or if they mark zones of intense magnetic activity shaping the flow of gas. You hover near one of these dark lanes, feeling its stillness like the quiet pause between two verses of a lullaby. Closer now, you can almost imagine brushing your fingertips along the fine grains of interstellar dust, though of course it's far too diffuse to feel. Oddly enough, the dust here is made of silicates, carbon compounds, and microscopic bits of ice, a delicate mix that's both cosmic debris and the raw material for future worlds. Quirky fact: in some nebulae, the dust grains may be coated with frozen ammonia or methane, a cosmic frosting that would be utterly useless on cupcakes, but perfect for seeding new chemistry. Fringe theorists speculate that these icy coatings could carry complex organic molecules, potentially scattering the building blocks of life through star-forming regions. You drift toward a bright knot in the nebula, a proto-star hiding inside a cocoon of gas. Its glow is faint but steady, and the surrounding material swirls toward it like moths drawn to a porch light. The swirling isn't random. There's a gentle, almost hypnotic rhythm to it, as though the whole nebula is breathing. Historians still argue whether stellar winds or supernova shockwaves from older stars are the main sculptors of these forms, carving cavities and filaments into the luminous clouds. You can see the results regardless: arches of glowing hydrogen, arcs of ionized oxygen, subtle gradients of light that would make any painter jealous. Farther on, you encounter the famous pillars shape, tall, towering columns of gas and dust, slowly being eroded by intense ultraviolet light from nearby massive stars. You float past their edges, where the light catches on ripples like sunlight on a slow-moving river. The columns are dense inside, hiding new stars that haven't yet emerged from their gaseous wombs. Fringe astronomers propose that the shape of such structures might depend on the balance between the surrounding pressure and the gravity of the clumps within, meaning that a slight change in conditions could have created entirely different forms. It's a reminder of how delicate and impermanent even the grandest cosmic scenery can be. The colors shift subtly as you pass from one nebular region to another. A patch dominated by ionized hydrogen glows a soft crimson, while pockets rich in oxygen shimmer with pale blue light. You can almost imagine the nebula humming at different pitches, each color vibrating with its own frequency. Quirky fact: these colors aren't always what you'd see with your naked eyes. They're often invisible wavelengths, mapped into visible colors by astronomers so humans can appreciate them. So, what you're seeing is as much an act of translation as it is observation, a cosmic bedtime story told in hues. You glide along a narrow channel where gas streams in slow, continuous motion toward a forming cluster of stars. The movement is graceful, like molasses sliding down an invisible slope. Historians still argue whether such flows are driven mainly by gravity or if radiation pressure from nearby massive stars plays the bigger role. It's a quiet debate, but one with big consequences for how we understand star formation. You simply let the sight wash over you, unbothered by the details, watching the slow ballet of particles. Ahead, an unusual sight catches your attention. A small, isolated nebula, glowing faintly in blues and purples, far from the massive star-forming regions. Fringe theorists call these orphan nebulae, suggesting they could be remnants of ancient supernovae drifting alone through space. Some think they may eventually dissipate entirely. Others believe they might collide with denser regions and spark new star formation. You drift around it slowly, the glow wrapping around you like a dim nightlight. The deeper you float into the nebula, the more you sense its layered structure. There are dense knots hiding in its heart, where temperatures drop low enough for ices to form on dust grains. Here, the quiet is almost absolute. No stellar winds, no bright light, just the slow ticking of cosmic chemistry. Quirky fact: in regions like this, complex molecules such as formaldehyde and even amino acids have been detected, quietly assembling in the dark. You smile, thinking of the irony. Life's ingredients forming silently in places no human will ever set foot. Finally, you pass through the nebula's outer edges, where the gas thins into delicate veils. The colors fade, the light dims, and you find yourself back in the broader void, carrying with you the memory of colors that might never have existed without the patient interplay of gas, dust, and gravity. Somewhere in the darkness ahead, more nebulae wait, each holding its own mysteries, patterns, and arguments for the historians and scientists who love to debate them. But for now, the afterimage of those glowing clouds lingers behind your eyelids, soft and reassuring, like the memory of a dream you're not quite ready to wake from. You leave the nebulae behind, their gentle glow fading into the background, and drift toward regions where the darkness feels thicker. Yet here, in the quiet, something monumental is about to happen. The first true stars are on the verge of waking. These are the legendary Population 3 stars, ancient giants that will live fast, burn furiously, and vanish long before the galaxies you know today ever form. You're arriving at a moment the universe will never repeat. There's no fanfare, no sudden flash, just a deep, pregnant stillness, as though the cosmos is holding its breath. The matter here has been patiently gathering for millions of years, gravity pulling in hydrogen and helium until the pressure at the center of these dense clumps becomes almost unbearable. Then, slowly at first, nuclear fusion begins. Hydrogen atoms collide, fuse, and in that instant, light is born. Not the shy flicker of earlier photons, but the fierce, bright blaze of a newborn star. You watch as the first one ignites, a pale blue point that swells in brightness until it rivals entire nebulae. Quirky fact: these early stars may have been hundreds of times more massive than the Sun, so large that their lifespans measured only in a few million years. Historians still argue whether they formed singly or in small, tight-knit groups, like pioneer settlements in a cosmic wilderness. The light spreads outward in all directions, washing over nearby clouds, heating them, pushing them, reshaping the very landscape you've just traveled through. You feel the warmth, not physically, but in the sense that the darkness now has a focus, a beacon. Fringe theorists suggest that the very first stars could have influenced the formation of dark matter halos, subtly anchoring the large-scale structure of the cosmos. It's an odd idea, but not entirely impossible. In the early universe, physics was still experimenting with the rules. More stars ignite around you, as if one blaze encourages another. A domino effect begins, massive clumps collapsing, bursting into life, their ultraviolet light ionizing the hydrogen around them into glowing spheres. You glide through one such sphere, its edges shimmering like the surface of soap bubbles, only far more delicate. The hydrogen atoms here are stripped bare, their electrons scattered by the intense radiation. Historians still argue whether these ionized zones were primarily the work of single massive stars or clusters acting in concert. Whatever the truth, they become cosmic lanterns, marking the first great relighting of the universe since the cosmic dawn. Up close, these stars are breathtaking, blinding white-blue giants, their surfaces seething with convection currents that churn heat toward the surface. They spin faster than your mind can comfortably grasp, some completing a rotation in just hours. Quirky detail: at such massive scales, their gravity warps the space around them enough that light from their far sides bends slightly toward you. It's a subtle distortion, but it makes you wonder how much of what you're seeing is reality, and how much is gravity's playful trick. You hover near one, feeling its steady output of energy like a deep, resonant hum. The star's surface boils with storms that dwarf entire planets, while inside, fusion builds heavier elements: carbon, oxygen, even small amounts of iron, elements the universe had never seen before. You think of it like the first kitchen, opening in a cosmic town, serving recipes that will one day feed entire generations of stars and planets. And then, you remember, these giants are not eternal. In fact, they're racing toward their ends. Their enormous masses mean their fuel burns quickly, and in just a few million years, each will collapse, explode, and scatter its enriched contents into the surrounding space. Fringe theories suggest some might have ended in direct collapse into black holes without even a supernova, swallowing their own brilliance in an instant. Historians still debate how many followed each path and whether these early black holes later merged into the supermassive ones anchoring galaxies today. But for now, you drift through their light, letting it wash over you in soft, imagined warmth. The stars cluster loosely, separated by stretches of darkness that still hold quiet pockets of gas, untouched by ionizing radiation. In these darker regions, smaller stars may be forming, cooler, dimmer, and far longer lived than their massive siblings. Quirky fact: some of these smaller stars might still exist somewhere in the modern universe, quietly burning after more than 13 billion years. You think of them like elderly storytellers, still alive to tell tales of when the universe was young. You float away from the brightest cluster. You glance back to see their light shimmering faintly through dust lanes. The glow is already shaping its surroundings, carving cavities, triggering new waves of star formation in the distance. It's a chain reaction, a quiet but relentless spreading of light. Historians still argue whether this period, called cosmic rionization, happened evenly across the universe or in patchy bursts, like lanterns slowly lighting in a vast, dark field. The void ahead is not so empty anymore. It's dotted with new points of light, each the result of gravity's patience, fusion's inevitability, and the universe's quiet insistence on making something out of almost nothing. You drift toward the next cluster, knowing some will soon vanish in spectacular deaths. But for now they shine, serene and unstoppable, marking the universe's first great act of creation after its long, dark youth. And in their glow, your own, thoughts feel quieter, steadier, as if the stars themselves are lending you their calm. You drift onward into a universe now peppered with the bright embers of first-generation stars, their light reaching farther and farther into the surrounding darkness. But here, something new emerges. Structures so large and intricate that you almost have to squint your imagination to take them in. The early galaxies are taking shape. They're not yet the majestic spirals and tidy ellipticals you might see in modern astronomy posters. No, these are rough drafts, clumps of stars, gas, and dust bound together in loose, awkward configurations, like teenagers still figuring out their posture. The first one you approach isn't a spiral at all. It's an irregular swarm of light glowing faintly with the combined radiance of millions of stars. Some parts seem denser, while others are stretched thin, as though the galaxy hasn't decided what shape it wants to be. Historians still argue whether such irregular forms were the result of chaotic mergers, smaller clumps colliding and blending, or simply the natural consequence of starting with a patchwork of gas clouds. You float along one edge, where faint filaments of matter stretch toward neighboring proto-galaxies, like bridges connecting distant cities. Inside, the scene is lively, in the quietest possible way. New stars are forming in dusty pockets, their light hidden until stellar winds carve out windows through the haze. Quirky fact: in these early galaxies, star formation rates were wildly high, sometimes 100 times faster than what the Milky Way manages today. That means vast numbers of massive, short-lived stars flaring to life and dying quickly, enriching the galaxy's gas with heavier elements at a pace that seems almost impatient. You drift past one of these bustling star-forming regions, where clusters of blue giants huddle together, bathing the surrounding gas in ultraviolet light. Farther out, you find something stranger still, a proto-galaxy already showing hints of spiral structure. The arms are faint and patchy, not the clean, sweeping arcs of modern spirals, but the suggestion is there, a skeletal blueprint for what will come billions of years later. Fringe theorists suggest that such early spiral patterns might have been triggered by uneven distributions of dark matter beneath the visible stars, acting as a hidden scaffolding. It's a bold claim, and historians of science still debate whether dark matter's influence at this stage was gentle or decisive. As you drift between these galaxies, the space feels busier. There are faint streaks of light where gas flows along, the filaments of the cosmic web feeding the growing structures. You catch glimpses of collisions, two proto-galaxies slowly spiraling into each other, their shapes distorting, their gas clouds smashing together and igniting bursts of star formation. Quirky detail: while these mergers seem violent, they happen so slowly that from your perspective they're more like an awkward but inevitable dance, each step measured in millions of years. You pass close to one such collision. The stars themselves rarely collide. Space between them is vast, but their combined gravity pulls the galaxies into a shared, chaotic orbit. Streams of stars arc out into long tidal tails, glittering ribbons that curve back toward the merging cores. Historians still argue whether most modern galaxies formed through many such small mergers or a few spectacularly large ones. Whatever. The answer, the result, is the same. Each merger shapes the galaxy's future personality. In one quiet corner of this early cosmic neighborhood, you spot a compact, spheroidal galaxy, already dense with old stars. Its light is warmer, yellower, hinting at an earlier burst of star formation, now long past. The stars here move in random orbits with no spiral order, as if the galaxy prefers the comfort of quiet stability. Fringe theories suggest that such early ellipticals may have formed in isolated regions, away from the hustle of frequent collisions, allowing them to settle into a relaxed, almost sleepy state. You drift outward again, and the larger structure becomes clear. These galaxies aren't floating alone. They cluster in groups, bound together by shared gravity. Between them lie vast voids, empty regions stretching for millions of light years, their darkness only occasionally broken by a faint wandering star. The arrangement is intricate yet oddly familiar, like a three-dimensional city map where each galaxy is a glowing district. Historians still debate whether the clustering was entirely random or subtly guided by invisible currents of dark energy. Quirky. Fact. Even in these early days, some galaxies already hosted supermassive black holes in their centers, millions of times the mass of the Sun. No one knows exactly how such giants formed so quickly. Fringe theorists imagine runaway growth from the collapse of the very first massive stars, while others point to direct collapse of huge gas clouds. You pass one such galaxy, feeling the faint pull of its central black hole, an invisible anchor around which the stars swirl in slow, hypnotic orbits. The farther you drift, the more galaxies you see. Some isolated, some bound together, some in the process of merging into larger shapes. The variety is mesmerizing. You think about how, billions of years from now, these rough, awkward forms will settle into the elegant spirals, tidy ellipticals, and dramatic irregulars that fill today's telescopic images. But for now, they're still finding themselves. And in their imperfection, there's a kind of beauty that feels honest, unpolished, patient, and endlessly creative. As you move beyond the cluster, the light from these young galaxies softens, fading into the background of space. You carry their shapes with you, blurry spirals, chunky ellipticals, bright irregulars, as a reminder that even the grandest cosmic structures began as experiments, trial runs, and happy accidents in the slow game of galactic evolution. Somewhere ahead, stars will settle into quiet routines. But for now, the universe still hums with restless energy, pushing forward into the next act. You keep moving, passing the scattered clusters of young galaxies until the universe feels less frantic. The light here is steadier, less like fireworks, and more like the low, comforting glow of a campfire at the end of the night. Stars have matured. They're no longer all massive, short-lived overachievers burning themselves out in a few million years. Now, you drift alongside a more measured rhythm, the quiet life of ordinary stars. You approach one such star, not unlike our sun, and feel the calm, steady warmth radiating outward. Its surface boils gently, granules rising and falling like the bubbles on a pot left to simmer rather than boil over. The core works at a patient pace, fusing hydrogen into helium, generating just enough energy to keep itself stable. Historians still argue whether our sun is exceptionally stable or merely average compared to other similar stars. Either way, it's this predictability that allows planets, when they're lucky enough, to host life. Quirky fact: stars like this often have magnetic cycles, flipping their magnetic poles every decade or so, a kind of slow-motion somersault that can cause bursts of activity on the surface. You watch as a magnetic tangle snaps, flinging a flare of plasma into space. In human terms, it's like a very grumpy stretch after a long nap. Brief, noisy, but over quickly. Not every star here is playing it cool. Some are in the prime of life, but like to throw the occasional tantrum. You glide past a red dwarf, smaller and dimmer than the sun, but with an unpredictable streak. Out of nowhere, it hurls a flare so bright that it temporarily outshines its own surface. Fringe theories suggest that some red dwarfs might be able to sustain this kind of outburst for days, bathing nearby planets in a constant solar storm. Whether those planets could still nurture life is a matter that keeps exoplanet researchers arguing late into the night. Deeper into this stellar neighborhood, you find pairs of stars locked together in orbit, exchanging material in a slow, intimate dance. Some of these binary systems are stable companions, shining steadily for billions of years. Others are less harmonious. In one, a bloated red giant overflows its boundary, spilling gas onto its smaller, denser partner. You watch as the smaller star greedily devours the stream, heating up and glowing fiercely. This kind of relationship usually ends in drama, sometimes even an explosion. Historians still debate whether certain rare supernova types are born solely from such stellar codependency. Between the stars, dust still lingers, but it's no longer the chaotic debris of the early universe. Here, it's neatly organized into disks or faint clouds, occasionally lit from within by a young star. These are the quiet nurseries where planets may be forming, tucked safely away from the violent collisions and constant reshuffling of the early cosmic ages. You notice another quirky detail. Not all stars follow the neat, spherical look you'd expect. Some spin so fast that they bulge at the equator, their shape more like a squashed pumpkin than a perfect sphere. One blue giant you pass has its equator flung so far outward that its poles shine brighter than its middle. Fringe theories even suggest that, in extreme cases, such fast-rotating stars might one day fling off a ring of material, Saturn style, creating temporary disks of light. The further you drift, the more you notice subtle variations in stellar personalities. Some stars pulse gently, their brightness rising and falling in regular cycles. Astronomers use these pulses like cosmic clocks, measuring distances across the galaxy with uncanny precision. Others barely change at all, staying so consistent that they could be mistaken for points of unchanging light, if not for the slow drift of their positions over millions of years. In one quiet corner, you find a globular cluster, an ancient gathering of hundreds of thousands of stars packed tightly, together in a shimmering sphere. Most of these stars are far older than the sun, their light cooler and more golden, like an eternal sunset. Historians still argue whether these clusters formed alongside the earliest galaxies or were captured later, drawn in by gravitational tides. You drift through the outer edges, where the density of stars makes the night feel impossibly full. There's something soothing about this stage of the universe. Stars are no longer rushing to be born or hurling themselves into violent death. They're keeping time on billion-year scales, each one a steady, glowing metronome in the grand symphony. The pace here is slower, but it's not static. Life, cycles still play out, just in a softer register. Somewhere ahead, the quiet will give way to the roar of collapse and explosion. But for now, the cosmic sea feels like it's breathing evenly, waiting. As you drift on, the calm begins to shift. You catch sight of a massive star nearing the end of its peaceful stretch, its surface swelling, its color warming from white-blue to yellow to red. It's not panicking, yet. But the subtle changes tell you that this star is about to enter a more dramatic chapter. And if you've been paying attention, you know what comes after swelling. You're about to leave the realm of serene starlight and step into the raw theatrics of the cosmos. The quiet warmth of stable starlight fades behind you as you drift towards something far less composed. Ahead, the light becomes fractured, bursts, flares, shimmering clouds of gas illuminated by energy so intense you can almost feel it prickling your skin, even from an impossible distance. You've reached the graveyards of massive stars, where endings are neither subtle nor silent. The star you've been watching swells to many times its original size, its outer layers glowing a deep, almost angry red. In its core, the hydrogen. Fuel has long since run out, replaced by heavier and heavier elements fusing in frantic layers. Historians still argue whether these late-stage reactions always follow the same chain, or whether small variations can push a star toward wildly different fates. Either way, the end game is inevitable. Gravity will win, and when it does, it won't go quietly. You hover at a respectful distance as the star's core collapses in milliseconds. The rebound is cataclysmic, an explosion so bright it briefly outshines its entire galaxy. This is a supernova, and it's both a destructive and a creative act. The shockwave rips through the star's outer layers, hurling them into space at thousands of kilometers per second. Those layers carry freshly minted elements, gold, iodine, uranium, that will one day be found in the bones of planets, in oceans, and, much later, in the molecules of human bodies. You probably won't survive standing anywhere near one of these, but as a distant witness, you're safe enough to admire the fireworks. A quirky fact: some supernovae are so oddly shaped that they appear to throw material in lopsided jets rather than in a perfect sphere. Fringe theories propose that strong magnetic fields or hidden companion stars might twist the blast into asymmetry. You watch one such explosion, its debris forming a strange double-lobed pattern like a cosmic butterfly that decided to glow in gamma rays. Not every stellar death is this spectacular. Smaller stars end in softer finales, gently shedding their outer layers to form planetary nebulae, delicate glowing shells of gas that expand outward for tens of thousands of years. The core, left behind, becomes a white dwarf, hot and bright at first, but slowly cooling into darkness. One such nebula drifts past you, its colors shifting from turquoise to rose as the central star pulses faintly. Historians still debate whether certain irregular nebula shapes come from uneven stellar winds or from planets once orbiting the dying star. And then there are the extreme oddities. You find yourself staring at the remnant of a particularly violent supernova, a neutron star. It's only about 20 kilometers across, yet it weighs more than the sun. Its surface is so dense that a teaspoon of its matter would outweigh a mountain. Some of these remnants spin hundreds of times per second, sending beams of radiation sweeping through space like lighthouse beams. This one flashes regularly, a precise cosmic clock ticking away the moments since its violent birth. Further ahead, you encounter a supernova remnant that's been quietly expanding for thousands of years. The once deadly shock wave is now a soft, ghostly veil of gas, threaded with delicate filaments. The universe here smells, if smells existed in space, of ozone and metal. This is the stardust stage, where debris from destruction becomes the raw material for something new. The atoms you're looking at will eventually find themselves in the hearts of planets, inside oceans, in clouds, or maybe even in the bloodstream of a living creature. A quirky historical note. In 1054 CE, Chinese astronomers recorded a guest star bright enough to be seen in daylight. That was a supernova, and its remnants still hang in the sky today as the Crab Nebula. Historians still argue whether medieval observers elsewhere also noticed it and simply failed to write it down, or whether atmospheric conditions made it visible, only in certain regions. And just when you think you've seen the most extreme endgame, you glimpse a core collapse so total that no neutron star remains, only a black hole. Its birth is violent, but the aftermath is strangely calm. There's no visible object, just the gravitational influence it exerts on nearby gas and stars. You'll get closer to these invisible giants soon enough, but here, among the wreckage of stellar death, you can sense the seeds of that next, stranger, chapter. The debris drifts outward, cooling, mixing with older clouds of interstellar matter. Gravity will eventually gather it into new clumps, starting the whole process again. You've just watched the cosmic equivalent of forest fires. Destructive, yes, but clearing the way for new growth. Somewhere nearby, dust is already condensing, whispering toward the birth of another generation of stars. You can't help but feel the cyclical pull of it all. Beginnings hidden inside endings. Endings hidden inside beginnings. The scene grows darker now, but it's not the peaceful, moonlit kind of darkness. This is a velvet black canvas with something lurking beneath, like an ocean at night when you know sharks are out there but can't see them. You're drifting into the realm of black holes, those invisible giants that never stop eating, theory. First sign you've arrived is a distortion in the starlight. It bends around an empty patch of space, warping the background like heat haze over asphalt. Historians still argue whether we've actually seen a black hole or merely its effects, because, by definition, light can't escape from inside. What we capture with telescopes is really the glow of matter spiraling toward doom. And here, you watch it in slow motion, a swirling accretion disk of gas and dust heated to millions of degrees, screaming in electromagnetic wavelengths that human ears can't hear, but your imagination happily translates into a deep, thrumming hum. The gravity here is intense enough to pull light into an orbit, and if you were reckless enough to cross the event horizon, well, let's just say your bedtime story would end abruptly, with you stretched thinner than a crepe. You probably wouldn't survive the process. Probably. A quirky tidbit for you. Some black holes are suspected to be wandering, not fixed at a galaxy's center, but roaming through interstellar space like solitary predators. Astronomers have spotted stars moving strangely, as though tugged by an unseen companion, and fringe theories suggest these might be micro-black holes, a kind of cosmic pocket monster that doesn't quite play by the rules. Your gaze drifts past a binary system where one star orbits a hidden partner. Gas streams from the visible star into a whirlpool around the black hole, creating bursts of X-rays whenever chunks of matter plunge inward. The scene is oddly hypnotic, like watching water swirl down a drain, except the water here is hotter than anything on Earth and moving at nearly the speed of light. Further out, you encounter a supermassive black hole anchoring an entire galaxy. Its mass is millions, sometimes billions of times that of the Sun. Yet from the outside, it looks like nothing more than a shadow at the heart of brilliance. Jets of high-energy particles erupt from its poles, reaching across light years like colossal searchlights. Historians still debate exactly how these jets form, whether magnetic fields are to blame, or if some deeper physics is at play that we haven't quite figured out. You can't resist getting closer to one of these jets. From here, the stream is blinding, a river of particles so fast that time itself seems to behave differently along its path. Fringe thinkers have even wondered whether such jets could carry information or matter across the cosmos, a kind of accidental intergalactic postal service, though no one's checking for mailboxes at the other end. And here's a more whimsical, historical fact. The idea of black holes existed on paper long before Einstein's relativity made them inevitable. In the late 1700s, a British geologist named John Michell wrote about dark stars whose gravity would be so strong that light itself couldn't escape. His notion was half forgotten for over a century before physics caught up to it. You pause in your drifting to notice something peculiar, a ring of light orbiting one of these monsters, the so-called photon sphere. Light here is trapped in a precarious balance, circling like a racetrack before either spiraling inward or breaking free. It's the kind of place that would make for spectacular cosmic tourism, if only it weren't lethally close to oblivion. Here, in this place of relentless consumption, creation lurks in the shadows. Black holes help shape galaxies by regulating star formation, blowing away gas with their outflows, and stirring up material that might otherwise settle quietly. In their own twisted way, they're gardeners, pruning and shaping the cosmic landscape. As you drift on, the starlight behind you slowly unbends, the warped distortions smoothing out like ripples fading from a pond. But you can't shake the feeling of those unseen gravitational fingers still reaching across space, tugging at the edges of your path. The memory of the black holes stays with you, like knowing a predator's silhouette is just beyond the campfire glow. The darkness behind you gives way to something vast and delicate, like lace spread across an infinite table. You're gliding into the cosmic web, the largest structure in the universe, though calling it a structure feels strange when it's made of nothing you can touch. From your vantage point, the galaxies aren't scattered randomly. They're strung along immense filaments that twist and branch, forming intersections called nodes. These are superclusters, the great crossroads of the cosmos, each one holding thousands of galaxies like tiny gems embedded in invisible threads. Between the filaments stretch enormous voids, regions so empty they make the space between stars feel downright crowded. You hover near one filament, watching galaxies drift slowly along it as though on a conveyor belt. Historians still argue whether the universe's early expansion or the hidden hand of dark matter shaped these patterns. The mainstream says dark matter's gravitational pull drew the cosmic web into place, but there's always someone with a fringe theory. Maybe it's all the effect of primordial sound waves or even subtle ripples in space-time left over from before the Big Bang. Here's a historical note. The term cosmic web first appeared in the 1990s when computer simulations revealed this strange interconnected geometry. Before that, astronomers knew galaxies formed clusters, but they didn't realize the full tapestry until they mapped enormous swaths of the night sky. Imagine thinking you'd been looking at random sprinkles on a cake, only to find out the sprinkles form an elaborate mural. You drift closer to a node, where filaments converge like rivers meeting in a delta. The gravitational fields here are tangled but strong, pulling in new galaxies over billions of years. It's oddly peaceful to watch, grand motion on such a slow time scale that you could fall asleep between frames. Well, if you weren't already in a bedtime story, a quirky tidbit. There's an actual Great Wall in space. Well, actually several. These are massive walls of galaxies, stretching hundreds of millions of light years. The Sloan Great Wall is one of the largest known. If you could hold it in your hand and ignore pesky things like mass and gravity, it would be as long compared to our Milky Way as the Milky Way is compared to your living room carpet. You glide down one filament like it's a glowing fiber optic cable, noticing that it isn't solid at all. It's more like a highway of gravitational influence. Gas, dark matter, and even light seem subtly channeled along it. Some astrophysicists suspect these filaments may funnel material directly into galaxies, feeding star formation like veins carrying nutrients into cells. Others aren't so sure, and the debate over exactly how matter flows here is still unsettled. As you pass into a void, the difference is startling. No glowing galaxies here, just sparse, lonely dots of light separated by tens of millions of light years. Some fringe thinkers have even suggested that voids could harbor hidden universes, tucked away beyond our observational reach. More cautious, scientists nod politely and then remind everyone about the importance of evidence. But even the emptiest spaces hum with faint cosmic background radiation, the afterglow of the Big Bang, like a ghost of the universe's childhood. It's a reminder that these vast empty patches are still part of the same fabric. You take one last wide look. From here, the web stretches in every direction, glowing faintly against the black, filaments fading into darkness beyond your sight. The whole thing feels almost alive, like neurons firing in a cosmic brain. Whether it's shaped by dark matter, primordial waves, or something stranger, it's the closest thing the universe has to a skeleton. Delicate, vast, and quietly holding everything together. From the cosmic web's filaments, you drift toward more intimate company, stars that defy the usual categories. Not the warm, friendly kind that shine for billions of years like your sun, but their eccentric cousins, the ones that make astrophysicists squint, shrug, and quietly update textbooks. The first oddball you meet is a neutron star. From a distance, it looks almost plain, just a small, dim point. But as you move closer, it becomes clear this is no ordinary star. Imagine cramming the mass of our sun into a sphere barely 20 kilometers wide. That's like squashing a mountain. range into a marshmallow-sized ball, only the marshmallow is so dense that a teaspoon of it would outweigh every skyscraper on Earth combined. You float near its surface, where gravity is so strong it would crush you into a smear thinner than a credit card. Historically speaking, neutron stars were first proposed in 1934 by Walter Baade and Fritz Zwicky, long before anyone knew they actually existed. It wasn't until 1967, when Jocelyn Bell Burnell detected a strange, pulsing radio signal, that the world got its first real proof. For a moment, her team even considered they might be hearing from aliens, until they realized the pulses were too perfect to be anything but a spinning neutron star. Historians still argue whether Bell Burnell's contribution got the recognition it deserved. Spoiler, it didn't. The Nobel went elsewhere. As you drift around the neutron star, you catch sight of a different creature, a magnetar. If neutron stars are heavyweights, magnetars are their eccentric rock star siblings. Same dense body, but with magnetic fields 1,000 trillion times stronger than Earth's. Even from a safe distance, their fields could wipe your phone's memory, scramble your brain's signals, and make your compass spin like it's had too much caffeine. Fringe theory lovers whisper that magnetars could theoretically power interstellar civilizations, though they'd have to mine energy from a star that could vaporize them. Farther on, you find a white dwarf, a faint, glowing ember of a once bright star. These stellar remnants aren't flashy, but they're quietly fascinating. The first white dwarf discovered, Sirius B, was spotted in 1862, orbiting the much brighter Sirius A. Astronomers were baffled at first. This tiny companion had the mass of the Sun, but was barely the size of Earth. The physics behind its existence wasn't understood until the 1920s. And even now, historians still argue over which scientist should get credit for the theory of electron degeneracy that explains their stability. You pass through a graveyard of white dwarfs, noticing some are covered in odd patches of metal. These are the remains of shattered planets and asteroids, their debris raining down onto the dead star's surface like cosmic confetti. It's a grim reminder. Even worlds can end up as nothing more than dust on a star's tombstone. Here's a quirky tidbit. There are zombie stars out there, white dwarfs that have exploded as supernovae but somehow survived the blast. Instead of dying completely, they limp on, smaller and stranger than before, like the universe's version of an action movie hero who definitely shouldn't have made it to the sequel. A little farther, you encounter something that feels even weirder, a pulsar. Technically, it's just a rotating neutron star, but it's shooting beams of radiation into space like a cosmic lighthouse. As it spins, the beams sweep across your position, flashing with metronome precision. Some pulsars spin hundreds of times per second, faster than a kitchen blender. The regularity of their signals has made them natural cosmic clocks, so precise that astronomers use them to measure gravitational waves. Hovering in this stellar freak show, you can't help but notice how peaceful they look from a distance. Even though up close they're violent, extreme, and wildly unstable, there's a certain elegance in their contradictions. Tiny but massive, dead but still dangerous, spinning faster than your ceiling fan but steady enough to keep time across galaxies. You drift on, leaving behind these strange remnants, wondering whether the universe creates them just to keep itself interesting. The space ahead grows hazy, not from cosmic dust blocking your view, but because that dust is busy, very busy, making worlds. You drift into a protoplanetary disk, a sprawling, slow-spinning pancake of gas, rock, and ice surrounding a young star. From here, the birth of planets looks almost casual, but don't be fooled. What you're seeing is one of the messiest, longest construction projects in the universe. Tiny particles bump into each other, stick, and slowly form clumps. Those clumps bump into more clumps, stick again, and soon you've got kilometer-sized planetesimals. Imagine cosmic snowballs, except instead of fluffy powder, they're made of silicates, iron, and the occasional frozen gas. And just like snowballs, The bigger they get, the more efficiently they sweep up smaller particles, growing into full-fledged planets over millions of years. Historically, the first clear evidence of a protoplanetary disk came in 1994, when the Hubble Space Telescope snapped images of them in the Orion Nebula. Before that, scientists were working mostly on theory and indirect clues. Historians still argue whether the concept truly began with Immanuel Kant in the 1700s or with Pierre-Simon Laplace's refined nebular hypothesis. Either way, you're floating inside proof that both men would have lost their wigs over. Near the star, the heat is intense. Here, rocky planets are forming. Dense worlds that could one day resemble Mercury, Venus, Earth, or Mars. You watch molten rivers of metal and rock swirl, collide, and merge into embryonic planets. Their surfaces boil, their skies are thick, with vaporized minerals, and yet somewhere in all that chaos, a future stable world is hiding. Farther out, where temperatures drop, you find icy giants in the making. These worlds start as solid cores, then greedily gather thick atmospheres of hydrogen and helium, becoming Jupiter-like gas giants or Neptune-like ice giants. Their orbits occasionally destabilize, sending them on wild migrations. Some get kicked out of their birth systems entirely, wandering alone through the galaxy as rogue planets. A fringe theory even suggests our own solar system may have lost one in its youth, a missing sibling flung into the dark. And then there are the strange ones. You spot a hot Jupiter, a gas giant that somehow ended up so close to its star that its atmosphere is literally being boiled away. It zips around its sun in just a few Earth days, like it's late for an interstellar meeting. Another oddball is a super-Earth, bigger and heavier than our planet, but still rocky, a world with more real estate, higher gravity, and possibly oceans deeper than Everest is tall. Among the dust lanes, you notice something else, spiral gaps in the disk. At first, they look like artistic flourishes, but they're actually carved by newborn planets, sweeping up material as they orbit. Like cosmic Roombas, they keep their lanes clean while the rest of the disk remains chaotic. A quirky fact for you: some stars have multiple planet-forming disks stacked like vinyl records, tilted at bizarre angles. Astronomers aren't entirely sure how these structures form, but one idea is that nearby stars' gravity can twist and warp disks into these improbable shapes. If true, the result could be planetary systems with orbits more like carnival rides than stable solar systems. As you drift farther from the bright young star, you pass into the colder reaches where comets are born. Dirty snowballs packed with frozen water, ammonia, methane, and the occasional trapped organic molecule. Some will stay here forever. Others will one day be flung inward, delivering water and life's building blocks to rocky worlds. Historians still argue whether that's how Earth got its oceans. You take one last look at the disk before moving on. It's messy, turbulent, and slow. But from this chaos will come worlds, moons, and maybe even life. The thought settles over you like a blanket. Somewhere, right now, billions of years away in both time and space, another system is being born under the same dusty light. You drift quietly into familiar territory, our own cosmic neighborhood. The sun burns steadily behind you, and planets wheel in their silent orbits. But tonight, you're not here for the headline acts like Jupiter or Saturn. No, you're going to poke around in the forgotten corners and odd little side streets of the solar system, the places where strange objects live their slow, underappreciated lives. Past Neptune's orbit lies the Kuiper Belt, a vast ring of icy bodies where dwarf planets keep each other cold company. There's Pluto, of course, once a planet, then demoted in 2006 by the International Astronomical Union. Historians still argue whether that decision was about scientific clarity or just academic politics. If Pluto had feelings, it might still be bitter, but it's not alone out here. Makemake, Haumea, and Eris also drift in the frozen dark, each with their own moons and mysteries. Haumea, for instance, spins so quickly it's been stretched into an egg shape, like the universe's laziest attempt at making breakfast. Closer to home, in the asteroid belt between Mars and Jupiter, lies Ceres, a dwarf planet with bright salt, deposits glinting in ancient craters. In 2015, NASA's Dawn spacecraft took close-up images of these reflective patches, sparking debates about whether they might hint at subsurface brines. A fringe idea even suggested Ceres could have harbored microbial life at some point, though that's still pure speculation. You turn toward the moons. Some of them are quietly stranger than most planets. Europa, orbiting Jupiter, has a smooth ice crust over a deep global ocean, an ocean possibly warmed by volcanic vents on the seafloor. Enceladus, a small moon of Saturn, shoots plumes of water, vapor hundreds of kilometers into space, practically inviting passing spacecraft to sample its chemistry. Titan, Saturn's largest moon, boasts rivers and lakes of liquid methane, plus a thick orange haze that makes it feel like you're walking inside a jar of smoked honey. And then there's Triton, Neptune's largest moon. It orbits backward compared to Neptune's rotation, which is basically the cosmic equivalent of walking the wrong way down an airport moving walkway. This hints that Triton didn't form here. It was probably captured from the Kuiper Belt. Now, frozen geysers dot its surface, venting nitrogen gas into the thin air. As you float past Mars, you remember one of the solar system's smaller oddities, its moons, Phobos and Deimos. They look like captured asteroids, lumpy and uneven, each barely hanging on to orbit. Phobos is spiraling inward toward Mars and will eventually break apart, possibly forming a temporary ring. If you're patient, say, wait a few tens of millions of years, you could watch it happen from here. Earth itself hides its own strangeness. Lurking just beyond our planet's main orbit are Trojan asteroids, small bodies that share Earth's path around the sun, but stay in stable points of gravitational balance. One was only discovered in 2010, suggesting we still haven't fully mapped our own neighborhood. A quirky historical note. In 1974, astronomers discovered 2060 Chiron, a small body orbiting between Saturn and Uranus. At first it was called an asteroid, then a comet, then something in between, a centaur. These hybrid objects blur the line between rocky and icy, and their unstable orbits mean they're just passing through this part of the solar system. You wander outward toward the Oort cloud, not that you can see it. This hypothetical shell of icy bodies may surround the solar system, extending halfway to the nearest stars. No spacecraft has ever reached it, and no telescope has ever photographed it directly. Historians still argue whether it's more a real structure or a convenient, mathematical explanation for long-period comets. Either way, if it exists, it's the solar system's ultimate attic, dark, cold, and full of things nobody's touched in billions of years. You glance back toward the sun, realizing how small its light seems from here. Our solar system might be home, but it's not tidy. It's cluttered with icy leftovers, odd moons, and mysterious travelers. The big planets may get the glory, but it's the strange little bodies that give the neighborhood its personality. You find yourself chasing a single photon, just one tiny packet of light, across the unfathomable distances of space. It's been traveling for billions of years without slowing down, slipping past galaxies and weaving through the gravitational fields of massive clusters. You, tagging along invisibly, feel the odd stillness that comes from moving at the speed of light. Time doesn't pass for your companion, though you're aware of every drifting speck and curve in space-time it encounters. Some photons are newborn, shining from the surface of a young star, bouncing off dust grains before breaking free. Others are ancient beyond comprehension, survivors from the very first moments after the Big Bang. That latter kind, cosmic microwave background radiation, was born about 380,000 years into the universe's life, when the first atoms formed and the cosmos finally became transparent to light. Before that, the universe was a dense, hot fog that scattered photons endlessly. Historians still argue whether this moment of transparency happened smoothly or in strange bursts, as if the universe flickered awake. You trail your photon as it slides around a galaxy cluster, subtly bent by the gravity of thousands of suns. This is gravitational lensing in action, a natural magnifying glass in space. Some fringe theories suggest that by mapping these bent paths precisely, astronomers could detect entire hidden populations of black holes or rogue planets. The mainstream view is more restrained, but still, the lensing effect has revealed galaxies, so faint and far away they'd otherwise be invisible. Photons can also be tricky storytellers. By the time their light reaches Earth, they may have been stretched, literally, by the expansion of space. What began as ultraviolet might now arrive as faint red or even microwave energy. It's like mailing yourself a bright blue shirt and opening the package to find it's faded pink. This redshift carries clues about the speed at which the universe is expanding. But there's still an open debate about whether the current measurements, based on different cosmic yardsticks, actually agree. Astronomers call this the Hubble tension, and it's one of today's juiciest unsolved puzzles. As you follow the photon farther back in time, you realize light doesn't always travel in straight lines, at least not from our perspective. The space it crosses is constantly stretching and curving under the influence of gravity and dark energy. Even small-scale structures, like clouds of intergalactic gas, can scatter or absorb light, dimming it before it arrives. Fringe ideas once proposed that maybe this tired light effect, rather than cosmic expansion, explained redshift. The consensus now is that's not the case, but it remains a quirky footnote in cosmology's history. You take a detour and drop into the quiet background glow that fills the universe. The cosmic microwave background hums softly at a temperature just above absolute zero. It's everywhere, inside your radio static, in every patch of night sky. Back in 1965, when Arno Penzias and Robert Wilson accidentally discovered it while calibrating a radio antenna, they thought they had pigeon droppings interfering with their data. It wasn't bird mess. It was the oldest light in the universe. Nearer in time, photons also carry stories from stellar explosions, from the violent deaths of supernovae to the whispery emissions of pulsars. Gamma-ray bursts, brief but blinding, can travel for billions of years before brushing past Earth. Some of these bursts may come from colliding neutron stars, events so intense they shake space-time itself. The photons from such an event arrive in step with gravitational waves, letting us see and hear the same cosmic moment. But not every photon's journey is so grand. Some are born in quiet, overlooked corners, a faint reflection from the ice on a comet, the soft glint of a moonlit crater. These low-energy travelers might never be recorded by telescopes, but they still wander the universe, unobserved messengers from places nobody's thought to look. Your single photon, finally, reaches its end, caught by the mirror of a telescope orbiting far above Earth's atmosphere. In that instant, all its billions of years of travel collapse into a single electric signal stored in a database, waiting for some graduate student to notice it. The journey is over, but its story, woven into the tapestry of light across the cosmos, will keep being told in the quiet rooms where astronomers work late into the night. You ease forward, letting the stream of photons fade behind you and drift into the slow, invisible tide of space-time itself. Out here, there are no walls, no floors, no obvious up or down, just the gentle curvature of reality. You feel the oddest sensation, space itself stretching beneath you, as though someone is quietly inflating an impossibly large balloon and you're glued to its surface. This is not movement through space. This is movement of space. Einstein's general relativity whispers in the background here, turning the universe into a vast, pliable fabric. Massive objects, stars, planets, black holes, are not just sitting in space. They're pressing into it, bending it. You float past a massive galaxy cluster and see its presence carved into the invisible geometry around it, the way a bowling ball would dent a trampoline. Historians still argue whether Einstein's contemporaries truly grasped the radical implications of his equations when he first presented them in 1915, or if they just nodded politely while thinking, "What in the world is he on about?" as you follow. A curve in the cosmic fabric, quantum physics sidles up with its strange grin. Space-time isn't perfectly smooth. It quivers at scales so tiny they make atoms look huge. Virtual particles blink in and out of existence, and the vacuum itself has energy. Fringe theories suggest these tiny jitters could be the seeds of the universe's structure, amplified during the first fraction of a second after the Big Bang. Others go even further, proposing that time might have a grainy, pixel-like texture if you zoomed in far enough. Mainstream physicists are cautious, but you can't help picturing the universe running on an impossibly complex cosmic game engine. Gravity waves ripple through your surroundings, faint, elongated pulses from colliding, black holes somewhere far away. They stretch and squeeze space by absurdly tiny amounts, yet here you can feel them as a gentle swell, like the slow rise and fall of an ocean. The first detection of these waves in 2015 was a triumph, confirming a prediction made a century earlier. Since then, astronomers have caught them from neutron star mergers too, creating a kind of multi-sensory cosmic weather report. You slide toward a region where space-time curves so sharply, it seems to fold in on itself. A black hole's event. Horizon. Out here, physics strains at its seams. Time for you slows relative to a distant observer, and if you tried to watch the outside universe, it would appear to speed up, stars flickering and fading in rapid succession. Fringe ideas toy with the possibility that such extreme warps could be gateways, wormholes linking distant points in the cosmos or even other universes. Whether that's real or just mathematically convenient science fiction, no one's sure. Far from these extremes, the everyday geometry of the universe still does something subtle. It changes the way light and matter behave over vast timescales. Cosmologists talk about the metric expansion of space, and you sense it as a slow, steady tug. It raises awkward questions. If space keeps stretching, does time stretch with it? Some physicists say no. Others argue that time and space are inseparable, bound to expand together. You get the feeling this is one of those questions that will outlive all of us. In quieter regions, you notice the almost imperceptible pull of dark energy, an unseen influence driving the universe's acceleration. The numbers are staggering. Roughly 70% of everything is this mysterious pressure, but nobody knows exactly what it is. It might be a property of space itself, a leftover from the early universe, or something even stranger. The fact that it exists at all is one of the great cosmic curveballs, and your mind keeps circling back to the thought that maybe, someday, someone will stumble across an equation that makes it all click into place. As you let yourself sink into this ocean of curved geometry, the boundaries between here and there start to blur. Distances lose meaning. Time feels elastic. Space becomes less like a thing you travel through and more like a living backdrop, slowly shifting and humming with quiet energy. You could stay here forever, but the faint light of familiar galaxies is calling you back, reminding you that even the most serene stretches of the cosmos are still part of an ongoing story. You drift gently toward the soft glow of human curiosity, leaving the warps and folds of space-time behind. There's a faint twinkle ahead, not from a star, but from glass, mirrors, and sensors, the eyes humanity has built to peer into the vastness. Telescopes line mountaintops, peering through thin air under the clearest skies. You float past one, perched high in Chile's Atacama Desert. Its enormous mirror turned toward a galaxy so faint you'd never spot it with your naked eye. Down below, a technician adjusts settings, sipping coffee at 2 in the morning because stars, annoyingly, refuse to show up during office hours. Then you drift higher, past the glow of cities, into the quiet reach of space where the Hubble Space Telescope still hums along, and farther still to the James Webb Space Telescope, its golden honeycomb mirrors unfolded like a flower in bloom. It catches light that's traveled for billions of years, revealing the early universe in crisp detail. Historians still argue whether Webb will be remembered as the single greatest leap in observational astronomy or merely the foundation for even wilder tools to come. Out on the moon's far side, a fringe proposal sits in limbo, a massive radio telescope built in a lunar crater, shielded from Earth's noisy signals. The idea is simple. Use the moon itself as a giant ear to listen for whispers from the cosmic dark ages before the first stars lit up. Nobody's built it yet, but just imagining the silence out there makes you shiver. You pass over a lonely Antarctic station where scientists operate neutrino detectors buried deep in the ice, catching ghostly particles that pass through your body and the entire planet without a single care. Nearby, an automated observatory clicks open its dome and begins the slow, deliberate sweep of the southern sky. Astronomy, you realize, isn't just about machines, it's also about people. You picture a tired grad student poring over data in the glow of a laptop, muttering at software glitches, or a veteran researcher in a sweater older than you telling stories about photographing Halley's Comet back in '86. Fringe figures pop into mind too, obsessive amateurs with backyard setups rivaling small observatories discovering comets before the pros even notice. Some of their names will never make headlines, yet their quiet contributions ripple through the scientific record. You drift through history's archive, past Galileo sketching the moons of Jupiter by candlelight, Caroline Herschel meticulously cataloging stars while her brother fiddled with lenses, and Henrietta Leavitt patiently measuring the brightness of variable stars. Work that helped map the scale of the universe. These moments are stitched into the fabric of exploration just as much as any spacecraft. The future of watching the cosmos seems almost too big to fit in your mind. Kilometer-wide telescopes, swarms of satellites, and gravitational wave detectors. So sensitive they could hear the quiet thud of black holes merging halfway across the universe. Some scientists dream of sending tiny probes to nearby stars, riding beams of light like cosmic surfboards. Others want to turn the sun itself into a giant magnifying lens, using its gravity to bend distant starlight. You let yourself hover above Earth, looking down at all the scattered observatories, radar dishes, and weathered rooftops where small telescopes point up in the dark. From here, the whole human effort looks like a network of flickering candles, each one trying to push back the infinite night. The thought is oddly comforting. No matter how vast or strange the universe is, there's always someone awake somewhere, eyes on the stars. The hum of data streams fades into a softer, slower rhythm. You feel the journey settling, like the final pages of a long book. The light around you warms, and your perspective shifts, not as a traveler through galaxies, but as a quiet observer, ready to let the cosmos turn without you for a while. You ease your breath, letting it match the unhurried pulse of the universe. The stars seem softer now, their edges blurring, their light stretching into long, gentle threads. Somewhere far away, galaxies keep spinning, but their motion feels like the slow drift of clouds. The air, if you imagine it, has that calm, still quality after a late summer evening rain. Your mind traces back through where you've been tonight, through the first sparks of the cosmic dawn, the dust and gravity, the quiet lives of stars, the webs linking galaxies. You realize that every part of it, every burst of light and silent drift, was simply the universe doing what it has always done, existing, expanding, and waiting for curious eyes to find it. Your shoulders ease, and the pull of thought grows lighter. You picture a single point of light in the distance, not rushing toward you, not fading away, just staying there, steady. The quiet hum of the cosmos is like a lullaby now, low and endless. The scene narrows, fading into the comforting weight of darkness. It's not empty here. It's full of calm, a gentle reminder that you don't have to know everything tonight. You can let the unanswered questions rest, so you close your eyes, not to block the stars, but to carry them with you into dreams. The universe will still be here when you wake. Sweet dreams.